Okay, so Wednesday we started looking at the magnetic properties of an electron gas. So we had the Hamiltonian. Well, it should be already boring for you that we are basically repeating the same things over and over again for various systems. Once you identify the Hamiltonian, you look at the energy values, and basically you need to sum, okay. So the physics, at least at low temperature, is kind of, let's say you have all these electrons without the magnetic field. For each kinetic energy value, you have two spin values. Since there's no magnetic field, there's no energy contribution from the spin orientation, so they both have the same energy level. But if you put the magnetic field due to this, the spin, electrons have a magnetic moment. Due to this magnetic moment, the electrons, they shift the energy. Some of them spin up, the electrons that have spin pointing in the direction of the magnetic field, their energy is lowered. The other electrons, their energy is increased. So the electrons, they shift, but basically the system will still try to minimize the energy. So the electrons whose energy values are shifted at t equal to 0, they will move shifted up. They will just flip their spin, and hence you get the magnetization. There will be more spin-up electrons at t equal to 0 or low temperature than spin-down electrons whose energy is higher. So you get the magnetization of the system.
So while shifting spin, the electrons will release energy as photons, right?
Sure.
Okay. The other question is...
Well, you see, since we are doing statistics, we are looking at all possibilities, and for a given configuration, once the system is in equilibrium, what is the most probable configuration? That is, we are looking. We are not looking at the changes in the system.
Okay.
But what you will actually see in a real system, you have your system, you turn the magnetic field on slowly. First of all, this is no longer an equilibrium system. But of course, you can turn the magnetic field slowly, and then you will start seeing the energy flips. So those flips will basically be emitted as light, as photons.
Okay, the other question I want to ask is, you said, while shifting after higher magnetic fields, we said that the Fermi energy level is getting slowly decreased.
No, initially the Fermi energy, if you, for a small magnetic field, Fermi energy will just stay where it is. But just look at the extreme case of, let's say, two electrons and the ground state without magnetic field. One will be spin up, the other one will be spin down. When you put the magnetic field spin up, its energy values will get lower and lower. Spin down will flip. It will also become a spin up. So it will also be a spin up state. If you increase the magnetic field, it shifts the energy to lower and lower values, and hence the Fermi level shifts down.
No, I want to ask is what we mean by the higher magnetic field. Is it the point that the lowest downspin energy is higher than the Fermi energy?
So what is the question? Let's start with that one.
So are we calling the point that the Fermi energy is lower for high magnetic field? Is it that magnetic field that causes the minimum energy of the spin down is exceeding the Fermi energy level, or different?
Well, high magnetic field on its own doesn't really mean anything. You have to compare it with something else. So what would you like to compare it with?
So we can't.
So let's say that you can say that, okay, magnetic field has this energy. If you put an electron in a magnetic field and spin in a magnetic field, this will be the energy, potential energy. You can compare this with Fermi energy. You can compare this with thermal energy. So magnetic field can be large compared to thermal energy, but small compared to the Fermi energy. So what would you like to compare it with? So if you're asking the question, at what values of the magnetic field do we start to see a shift in the Fermi energy? Well, then you are practically asking me to compare the magnetic energy with the Fermi energy. Other questions? And okay, this is basically what is happening over there. Then you have to put in some numbers. The magnetization is nothing but the magnetic moment of the system. Spin up has positive magnetization, spin down has negative magnetization, so the total magnetization from all the spins is just given by this expression over there. And the next task will be what is n plus and what is n minus. So you're just trying to count them. The numbers, the number is determined by the chemical potential, which at zero temperature is the Fermi energy, which we already know. Well, the rest is, okay, it's at t equal to 0, the system is simple. At small t, well, things start to get a bit more complicated, which I just wanted to skip. I do advise to go over the derivation details in the book. And today I would like to discuss what happens. You see, if you consider the electrons, they basically there are two phenomena that contributes to their magnetic properties. One is their spin. Each electron practically behaves like a small magnet. The other property they have is their motion. If you have a charge in motion, it creates a magnetic field. So this motion will also create, if you ask me the question, oh, what is the magnetic field of the system? Well, I have to take into account both contributions, one from the spin, the other one from this motion of the electrons. Now, the spin, well, they are just small. If we are treating electrons as very small magnetic dipoles, they will try to align with the magnetic field itself. So you get a positive magnetization. If you put your electron in a electron gas in a magnetic field, you would obtain a positive magnetization due to the spins of the electrons. Now, things get a bit more complicated if you look at the motion of the electrons. So, for example, let's say that if these were not free electrons, but just electrons orbiting the atom, again, we have both of those phenomena in the atom. One is the magnetic field due to this orientation of the spin, but there is also the magnetic moment of the electrons due to their orbit around the atom itself. So it's orbiting the atom, so it has a magnetic dipole moment. You can just imagine it as a very small closed loop, current carrying loop. Now, when you put this atom in a magnetic field, you can either move the atom itself, or you can just turn on the magnetic field slowly. Then do you remember Lenz's law of induction? What is it?
I probably don't recall the name. I need to see.
Okay.
Apply the current. If you apply an external current or magnetic field, and the material itself aligns itself to create an induced current in the opposite direction of the field, depending on if it's a diamagnetic or paramagnetic.
Well, somewhat, let's say, not precisely, but the Lenz law basically tells us that the induced current will be such that it will try to cancel the effect creating it. So let's say you have your atom over here, you put the atom in a magnetic field, the induced electric current will try to reduce the magnetic field, so it will be pointing in it will create a magnetic field that is pointing in the opposite direction of the applied magnetic field. So the alignment of the spin will enhance the magnetic field, whereas this effect, the diamagnetic effect, will try to reduce the magnetic field, and this will be created by the motion of the electrons. So let's study that problem now. So that is what I would like to study at least this hour. Well, the Hamiltonian we have is p squared minus p minus e over c squared. Now, this time I'm just ignoring the spin degrees of freedom, just looking at the motion of the electrons. And you can choose A to be 1 over 2 r cross B. B being B0 in the z hat direction. And in fact, I do advise you to study this problem somewhat in detail. You can convert this problem to a harmonic oscillator problem, whose solutions we already know. And the energy level, so you see, if you think of this problem classically, you have a magnetic field in the z direction, and you just have a bunch of electrons within this magnetic field. So if you send an electron to this region of uniform magnetic field, what they will do is the velocity, there won't be any acceleration in the direction of the magnetic field. So the component of velocity in the direction of the magnetic field will be constant, but there will be a force perpendicular to the horizontal component towards the center. So in the direction perpendicular to the magnetic field, it will do a circular motion. Along the magnetic field, it will be just a uniform motion with constant acceleration. So it will basically follow an helix. And so if you solve this problem, this is what you get. You see, this is the harmonic oscillator part. And the z motion is just basically free particle. Now the quantization in the x and y direction is kind of expected. You have a closed orbit just like around the atom. In fact, you can actually apply the Bohr model. So if you would like to study this two-dimensional motion using Bohr's approach, basically we have two conditions. One is the angular momentum should be a multiple of h bar, which just if you just imagine circular orbits, PR should be nh bar. On the other hand, the central force causing this circular motion is just the magnetic force. Well, the velocities just cancel, so we have P over R is equal to E times B. Well, if you just multiply them, P squared is equal to NH bar B. Sorry, this is E over C in these units. So P squared over 2M is given by this number. And a multiple of H bar B over 2MC. Oh, of course, there's also E. Basically, you get this factor, more or less. Well, it's not the exact answer, but the order of magnitude is basically correct. You get more states that actually exists, but you do recover the formula. And this is this circular part. This is the part describing the motion along the magnetic field. Now, there's a degeneracy. You see, at least the approach in the book is, let's say, this is the V equal to 0 case. All these energy levels. You would expect the physical properties to change continuously as a function of P. You don't expect them to change just from discontinuously. A very small B you shouldn't be able to detect. So what actually happens is, as you increase B, if you look at this number over here, just let's ignore the Z component of the motion, suddenly you have some discrete states. The splitting between the states is proportional to B, so in the limit as B goes to 0, you again recover basically the continuum of states. So what actually happens is, these continuum states, they essentially group together corresponding to different values of J. If this is J, this is J plus 1, this is J minus 1. So somehow these continuous states on the left, when you turn on the magnetic field, they group together and each one corresponds to a given value of J. Now, as you can see, there are more than one state for a given value of J, which will be the degeneracy. Well, the approach in the book is, let's just count the number of states here. Let's count how many states are there here. And that will basically give me the degeneracy corresponding to a given J value. Well, how can we do that? We already know how to count the number of states, at least in phase space. It is dx, dy, dpx, dpy divided by h squared. Again, I'm just looking at the two-dimensional motion. The motion in the z direction is already over here. It's separate. This is equal to the size along the x or the y-axis divided by h squared. Now we can go switch to circular coordinates, which will give me a 2 pi dp squared. Well, let me just divide by 2m and multiply by 2m. This is Lx, Ly divided by h squared, 4 pi m d epsilon. Well, the energy difference between these states over there is just J changes by 1. It's just E h bar b over mc. So degeneracy of each J is given by Lx, Ly 4 pi E h bar b over h squared c. Which, okay, so, okay, h bar is h over 2 pi. So this cancels one of this, and there's a factor 2 over there, 2EB HC. Okay, apparently I have a mistake of a factor of 2. Hmm? 2 pi is already over there. Because it's the angular integral. I'm integrating over 2 pi. And p squared over 2m is the energy, so that brings me another factor of 2m. So it's 4 pi m, the prefactor, and the change in energy between two successive values of J is AH bar B over MC. Okay, I don't see why I am missing a factor 2. I have an extra factor 2, sorry.
Alexander and Y are just the lengths in the physical space. But for which side I don't know.
Well, you see, this is my volume. This is the magnetic field. This is Lx.
Okay,
this is Ly. This is Lz.
Okay, this is the volume the thing happens.
My gas is within a volume. Lx, Ly is basically the cross-sectional area perpendicular to B. It doesn't even have to be actually cubic or rectangular.
Hocam, where did we get 2 pi at the beginning?
Well, you see, dpx, dpy.
Okay.
This is d phi p dp. Yes, now I know the
We
problem.
wrote that
Which
dp
is
squared.
2 pi dp squared over 2. So here when I write it as dp squared, there's a 1 over 2 over there. So this is the degeneracy of each j. Well, there is a somewhat intuitive argument to obtain this degeneracy, more or less this degeneracy, not the exact number, but the dependence. Well, let's look at this Bohr's approach to this problem. You see, I have these two equations. When I multiply them, I got the energy. If I divide them, it's PR over P over R. This is NH bar over EBC. This is R squared should be NH bar C over EB. Well, this is R is the circular orbit of the electron. Pi R squared is the area. So here you see the orbits enclose an area which is a multiple of that area quantum, in a sense. The area quantum is given by NHC over 2EB. Well, if I have a total cross-sectional area of Lx, Ly, the number of area quantum I can fit within this area will be Hc over 2Eb, Lx, Ly, Eb over Hc times 2, which is basically the same number, up to a factor 2. Again, it doesn't give the exact correct answer, but still intuitively it gives you an idea of what's going on. Now, basically, we have everything we need to study this problem. We need to look at the grand canonical partition function, which, remember, this is nothing but a sum. Since these are fermions, this is the sum over single particle states of logarithm of 1 plus z e to power minus beta epsilon, epsilon being the energy of this system. Now, the single particle states are given by a z component of momentum. Let's say this is Lz dpz over h. I'm summing over the z momentum and z position. Then I have the sum over j. If a particle has a given j value and has a given pz, every state having the same j and same pz, they have the same energy, and we already know that we have Lx, Ly, Eb over Hc. Such states, this is the degeneracy of logarithm of 1 plus z exponent of minus beta E h bar b over mc, j plus 1 over 2 plus pz squared over 2m. Or minus beta. So this is my partition function. Now practically I know everything about the system. Of course the question is, okay, what does this equation tell me about my system? Now, what I would like to know is, okay, there's the chemical potential. The first question we can ask, what happens at small values of Z, which we already had seen that it corresponds to high temperatures. If Z is much, much less than 1, then what we can do is the second term in the logarithm is small. So we can do a Taylor expansion of the logarithm. So this partition function becomes the volume of the system. Well, you see we have Lx, Ly times Lz. That gives me the volume of my system. I have Eb over Hc, h squared c, times integral over Pz from minus infinity to infinity, sum over j from 0 to infinity, and I have z times that exponent, minus beta E H bar B over MC J plus 1 over 2 minus beta PZ squared over 2M. Now I can evaluate the PZ integral. PZ integral will just give me square root of pi 2M kt. Now this should be already familiar to you. This factor is nothing but 1 over lambda, the thermal wavelength. And we have a summation over J. There is a Z over here. We have the exponent minus beta E H bar B over MC J plus 1 over 2. I can evaluate the sum over J. V E B over HC. There's a 1 over lambda. We have the Z. We still need to calculate what Z is. So what is that summation? This is a constant term. The rest is just some number raised to the power j. So that sum is nothing but 1 minus whatever that number is. Which will be V over lambda EB over HC Z times 2 over sine hyperbolic minus beta E H bar B over 2MC. And plus. This is our partition function for the system. What is N? The average number of electrons of my system. How can I calculate that in terms of Q? Z differentiate with respect to Z of the logarithm of Q. Let's go back. This was my Q. You see, I wouldn't like to use this one. If I didn't do something wrong, if you differentiate with respect, if you take the logarithm of Q, differentiate with respect to Z, you just get 1 over Z. So probably we have done too much approximation to obtain that value, that N. But I can go back, I can use this expression over here. Sorry. This is not the partition function. This is the Q potential. This is already the logarithm of Q. So this is, well, basically V over lambda, EB over HC, Z 2 over sine hyperbolic, whatever that number is. Well, Q potential basically turned out to be N. What about the magnetization? The magnetic field, magnetic moment of the system. Well, remember the Hamiltonian of the system would be, well, all the terms due to the kinetic energy minus m dot b. So I can write the magnetic moment as minus the derivative of the Hamiltonian with respect to b. Of course, I need to take the average. Now I have to somehow write this in terms of the Q potential. You see, this should be equal to sum over all states, single particle states of e to power minus beta, the energy, times minus the h over dB, 1 over Q. Not single particle states, by the way. This is sum of all microstates. Because I'm now writing the grand canonical partition function. That sum already contains all the number of summation over number of particles and the microstates, etc. Well, I can write this as 1 over Q, this sum of derivative of the exponent with respect to B. You see, if I take the derivative of that exponent with respect to the magnetic field, it will bring down a minus beta, so I need to multiply by KT. And then the derivative of the energy with respect to the magnetic field. And so this is nothing but KT times derivative of with respect to B of the Q potential. This is the magnetization of the system. Well, I know what the Q potential is. This is my Q potential. It's enough to take its derivative with respect to B to obtain the magnetic moment. And once you have the magnetic moment, you can calculate the susceptibility, which is given as the magnetization divided. Now the magnetic moment, okay, magnetization and magnetic moment, they are slightly different things. Magnetization is the magnetic moment per unit volume. Susceptibility is defined as, in terms of the magnetization, as B goes to 0. This is susceptibility. Again, we are looking at large temperature limit. Okay, I will skip the steps. You can calculate, well, basically you need to take the derivative of this expression with respect to B and then take this limit. By the way, this is nothing but the derivative with respect to B of M over V. You can look up the steps in the book.
This should be less than 0,
Hmm?
It should be less than 0, I guess.
Why?
Since we are studying the magnet.
Yeah. This turns out to be minus 5 mu effective divided by 3 kT. It is negative. It turned out to be negative. Well, not because it had to be diamagnetic. It is diamagnetic because this turned out to be negative. And this mu effective is basically E h bar over mc. Yes. 4 pi mc. No. 2 mc, sorry. Well, basically, I mean, it's straightforward. The physics is kind of already over. So we have identified the partition function. We know how to calculate the magnetization. We know how to from the magnetization, we know how to calculate the susceptibility and high temperature limit. This is what you would obtain. The crucial thing that, as we expected, this is negative. This is due to the motion of the electrons, and the susceptibility turned out to be negative. Well, there's the other extreme. What happens okay, this is what happened when the temperature was large. What happens at T goes to 0? Well, let's look at the steps will be more or less the same. You see, this is the Q potential, whatever the temperature is. This is the valid expression at all temperatures. Well, you can actually just go ahead and put it in a computer and just tell the computer to calculate those sums or integrals numerically, take whatever derivative you want, and you can actually study it exactly at all temperatures. Of course, you have to also tell the computer to solve for Z in terms of the number of particles, but it's something that can be done numerically. So what we are trying to achieve here is somehow to get a sense of what this equation tells us, at least at various limits. One was at high temperature, which is when Z is small. Now at low temperature, that we already know that it diverges. In fact, at T equal to 0, Z diverges, so we cannot really make that small approximation. But we can still try to replace this sum by an integral and try to evaluate those integrals. You see, if you straight away replace that J integral also by an integral, J summation, this becomes volume EB over H squared C dpz dj logarithm of 1 plus Z exponent minus beta E H bar, let me call that is J. I'm integrating over J, B over MC. This is J let me call it now, minus beta PZ squared over 2M Pz goes from minus infinity to infinity, J goes from 0 to infinity. Well, I can make a change of variable. Let me just call X as Bj. Then that term basically becomes VEB over H squared C dpz dx over B logarithm of 1 plus Z exponent minus beta E H bar over MCX minus beta PZ squared over 2M. B is cancelled. So you see that Q potential is independent of B. Now if B is 0, then there's no magnetization. Obviously, we are doing something wrong. Basically, what we are doing here is we are making an expansion. And this is the term which is independent of B. There are corrections to this expansion which will have a B dependence. And that B dependence can be calculated. You see, here what we had done was we replaced sum over J of a function that depends on J plus 1 over 2. we replace that with an integral. Let me call this x f of x from 0 to infinity. This is an approximation. Then we have corrections to that. And the first correction is 1 over 24 f prime at 0. Well, some of you were mentioning that we always end up having minus 1 over 12 everywhere. If you like, it's also here. Anyway, so this is the approximation. You see, the first term, the integral part, okay, we had already looked at the contribution from this one to Q potential. You see, the idea is we are trying to calculate somehow this Q potential over here. Well, it's a complicated expression. No, not that one. That summation over there. Now, to calculate that, we tried replacing that summation over J with an integration. You see, in the high temperature limit, it was easy to calculate that summation explicitly because we could expand, Z was small, we could expand that logarithm in a Taylor expansion, and with the first term we could just sum over J. Now, without that approximation, we have to somehow find a result for that J summation. If we replace it by an integral over here, there's no B dependence left, so the magnetization would be just 0. Remember, magnetization is nothing but it turned out that the magnetization is just the derivative of the Q potential with respect to B. So we have to calculate the next correction. The next correction comes from this term to that summation. And it is nice because it doesn't involve any summation, it doesn't involve any integration. So the PZ integral was basically trivial if we could get it out of that logarithm. But the summation over J was non-trivial. Now we don't even have that summation. And in fact, this is when J plus 1 is 0. Well, let me try to write it down. This is the Q potential that I'm trying to approximate. And this Euler formula, do you have an idea how you can get that? Think of the residue theorem. This is the residue theorem tells you that if you have an integration in the complex plane around a closed contour, the result of the integral is just a summation over the contribution of all the residues. So that summation, if you treat it as a sum of the residues, can you imagine a function that have poles at integer values or integer complex values? Where are the poles of this function?
Minus infinity.
No. At minus infinity,
Okay.
it's just 1.
And minus pi.
Hmm?
And
Pi plus 2 and pi. It should be pi, plus minus pi, plus minus 3 pi, plus minus 5 pi. Or let me write it slightly differently if I want to have integer values. Yeah, this function has, or let me even put an I over there. This function has poles at positive integer x. So if you write a loop integral around of this, some function multiplying this function. The residues will be at integer values, and the residues will be proportional to the value of whatever function is multiplying it, this function at those values of integers. So the loop integral will basically be the sum of sum over integers. Now, of course, you still need to play around a bit, and then you have to find some other means of calculating that integral, that summation. But we have already seen various approximations of the Bose-Einstein distribution, Fermi-Dirac distribution, which is basically this function over here. Anyway, let's continue with our approximation. You see here we have, if I just replace that J summation with an integration that is a term independent of B, then I will have plus 1 over 24. Well, I need to just take the derivative of this function, which will be V dpz over h squared c e b. If I take the derivative with respect to j, okay, so let me write it down. Z times minus beta e h bar b over mc times the exponent of minus beta pz squared over 2, and because I'm setting j plus 1 equal to 0, so there's no, this term just doesn't appear over there, divided by 1 plus z times the exponent. So this is the B-dependent part. Again, basically, take the derivatives to obtain the magnetization. You can calculate the susceptibility, and again, since susceptibility is defined as in the limit of vanishing magnetic field, you can practically set B equal to 0 in this integral. First you take the derivative with respect to B and set B equal to 0. And what will remain is an integral that we had already studied. This is just the Fermi-Dirac distribution. Anyway, I will skip the steps, leave you as an exercise. And let me just quote the result. Well, it's just minus the third of the Pauli paramagnetic susceptibility. So this is small. The magnetic susceptibility is still positive because it receives both contributions from both Pauli paramagnetism due to the alignment of the spins and also this result. But it's neither one nor the other one. But the crucial thing in this exercise that I don't really care if you don't remember this result. But can you follow the steps? You see, the basic idea is first you have to understand the physics. You see, that is probably the thing that makes this course, the statistical physics course, the most difficult course. You have to understand the physics of the problem. You have to understand the quantum mechanical or classical physics, but whatever there is, whichever problem you have to understand the physics. What are the energy eigenvalues? How can you use the physics of the problem to your advantage? If you remember what we did on last week, well, you have to know how the energies are shifted. You have to be able to interpret that. The electrons will just fill the unoccupied levels, so you get an unequal number of spin-ups and spin-downs. Well, basically the same thing appears over here. You have to first know the energy levels, their degeneracies. Once you know them, the rest will be carrying out summations and differentiation, which in principle you can just let the computer do. But of course, you first have to write down those equations using your physics knowledge of the problem. The computer can do that for you. But once you write down the partition function, basically the physics is over. The rest is how can you approximate or just let the computer do it. Any questions? Okay, let's give a break and go to the New Year party. And after the break, I will just make a sketch of what happens in white dwarfs. That is after the break.